Professor Kitain.
Doing good, Prof. How are you? How is it in Australia? They opened the border already.
They open in New South Wales and Victoria, but
Okay.
still we are close here. So because they reach both New South Wales and Victoria, Sydney and Melbourne, they reach 90% vaccination.
90. That's great. Okay.
Very plenty, double doses. But here only we have 65. There are a group that they won't like to be vaccinated, making problems. So, but hopefully by mid-December they will open. We hope.
Nice to hear that, Prof. Beltramini.
And how is the situation?
Let me introduce you, Dr. Siti, so like from ITS,
right?
Institute of Sepulu November. Sepulu November Institute of Technology.
Hello.
Yes. Hello, yes. Professor. We meet again.
Hello. How are you? Yeah, nice to meet you again. Yeah. Yeah. Everything okay?
Good.
Yes.
All right. So, Professor Beltramini, Dr. Siti, if you don't mind, let me start. It's already 12:55 here in Kumamoto, Japan. So, we will start our lecture. Professor Beltramini's lecture for today. So, at first, let me introduce Professor Beltramini. Professor Beltramini is from the Queensland University of Technology in Australia. So he is now an adjunct professor of the Center for Agriculture and Bioeconomy of Queensland University of Technology in Brisbane, Australia. So Australia, they opened the border already. So you can, to our students and the students of ITS, we can now visit Australia. So, all right. Professor Beltramini has more than 30 years of experience in the fundamental areas of petroleum refining technologies, solid-state catalysis, surface characterization, material science, reactor design, anything related to chemical engineering, also on catalysis. So for today, he will talk about biomass conversion processes for energy and chemicals, fundamentals, application, challenges, and opportunities. Without much further ado, let us welcome Professor Beltramini. Professor Beltramini, the floor is all yours. Okay, please.
Thank you very much, Professor Kitain, for your kind introduction. Okay, I will do the share screen.
Oh, yes.
Oh, yeah, you need to...
Prof, go ahead. Professor Beltramini, go ahead,
yes.
Please. You may share your screen.
All right. Yes, I would like to talk today on biomass conversion process for energy and chemicals, and gives an idea of the fundamental, the application that we can have, what are the challenge and opportunity. And this is a good discussion here because we are facing now a big problem with the climate change and also the idea to supply renewable energy and renewable chemical from renewable and phase out practically our condition that we are using with fossil fuel industry. Let me this here. Okay. What we're doing here in QUT is that we create what we call a strategy for creating a sustainable world, and we involve different institutions at the university and different departments, from the economical department, from the social science, from the medical department, engineering, of course, chemistry, and also industrial production. What we want to do here is mainly to create sustainability, and our first idea is to going into the community and tell the community what we can do and what are the probably innovative solutions that we can complement with traditional chemical industry. And then we can see what are the products and projects that we can offer and how we can get a more sustainable way of living. And here combining the economy of the region, the economy of the country and the world, and also join with industry players from the farming industry, agriculture, environmental group, and also the government players department that is on the policies. Just a brief introduction. This is part of our team that we are dedicating to this task. We have several students doing PhD in different topics of biomass. So why we are doing that? We are doing this is because we want to see the use of biomass and their resources and in a more effective way. For that reason, in the presentation today, I would like to establish some fundamental understanding on these characteristics of the biomass resources, how we can design the operation, where we need to design the operation, and what are the conditions for that, and covering some topicals that characterization of the biomass, different biomass resources, design aspect of the process, what are the steps of the process, and particularly is then how they will have the environmental impact of this process, and especially how we can study what we call the life cycle analysis. That this is one of the important things, that every part need to be put in this puzzle and they need to be being in an optimum condition in order to obtain what we want at the end of the day, that is sustainability. We are doing this because we know that the human condition is at a threshold at this moment, and we know what is going on in Glasgow, and we know also from different surveys that there are done during the year that there are two main problems that are energy and water. Energy, because we have a very growing population, and in 2050 we have practically double the population that we have now, but the demand of energy will be nearly triple that. And the other problem is not only the energy, it's the water, because the water we need water for a more sustainable existence, and also is a priority for any human being. The energy and the water then will have impact in the food and the environment, and we know that if we not solve this problem, we have more poverty in the world. Then there is the problem of terrorism of war, because people want to take in their hands what is not there, and for some good or bad reason they do that. They produce disease. We know what we are dealing in the last 2 years was very unexpected, but it's part of all of this change. So for that reason, the education in the population is very important. Three main topics here: the pollution, climate change, and resource depletion. This is something that we need to not to take lightly, and we need to look very well into all of these problem conditions. We know that during COVID, we have uncertainty what will be happening with the energy consumption, and especially with liquid fuel. This is an example on the liquid fuel. We have a very big drop. Everybody was content on that, and everybody was saying, yes, okay, we can control then the production of that, and we can decrease, and we can have a better life. But unfortunately, we see that now we are coming back to original conditions that we were pre-COVID, and especially is in still in the production of oil, gas, and coal. And there are already countries that they are accelerating that production in order that to have supplementary energy storage for the next 5-10 years. And we know that this is a big problem. We are recovering from this pandemic, but recovering from this pandemic is that we have a very high economic growth. And because of the impact of the COVID-19 in all the society and in the economy, is that the growth at the moment is accelerating. And the economic growth will be accelerating more and more, and will be reach just the condition, not solo on the value of the trillion of dollars, but also on the amount of energy that will be needed. As I said, we nearly will need to triple the amount of energy in order to supply what everybody needs, a good living condition. And this is all triggered because mainly industrial and electrical power are the ones that drive the increase in energy consumption. Historically, the industrial sector is the one that drives
Recording in progress.
in the energy consumption. And we see also that the transportation will be take some years, especially the air transportation will be take some years into recovery, still due to the uncertainty opening close of the country. In terms of residential and commercial, the increase is very minimal, but the important one is in the industrial point of view. The industrial point of view is the one that we need to reformulate the complete industry that we have now that is based totally on fossil fuels. So what we can say that COVID brings here is that the return to level of energy consumption will be take years, but still the emission of CO2 is increasing. We have the incentive to use renewable energy, but especially we need to take into account the cost of this technology because it's a big competition, and especially, for example, here in Australia, between the use of the renewable and the use of natural gas. We have plenty of supply of natural gas, but still natural gas is a problem due to the CO2 emission. Coal still is in the background because the coal industry is very important for the country, and especially for the coal export, especially to India and China. Nuclear power here is not in use, but is decreasing more and more in many countries due to the problem with nuclear. Although I'm not talking much on nuclear today, I want that favor the implementation of the nuclear technology because I think it's very safe. So in that case, we will have a continued increase of this energy. And one of the conditions we need to solve the problem of the energy is that we need to get a new strategy in order to produce energy in a sustainable way. In order to do that, we need to address the three questions that are the climate change, that we need to improve the air quality in many countries, and also we need to achieve what was the goal of the United Nations, that everybody have free access to energy, because energy is something sustainable that everybody needs in order to live. In order to do that, we need also to reduce the CO2 emission. And by this X scenario, we see here if we are doing what we are doing now with the new policy X scenario that we are implementing in the previous year, that will be increasing. The only way to decrease and to have zero emission by 2050 is that we need to introduce a big chunk and renewable, but not only that. The other nearly half of the pipe on that is that we need to have a very efficient process. We see here that renewables, nuclear, carbon sequestration will do the work, but we do the work halfway. If those processes are not very efficient, still will have the problem. And this is coming because the energy demand is growing exponentially, especially in developing countries. We see very clear here, United States, Europe, and Japan, they don't have problem. And by 2040, the demand of energy in those countries look like that will be decreased. It's not that will be decreased, it's that the level of energy will be the same than now, with the only difference is that they have more efficient process. So they are working on efficiency of present process. And that will be reduced the demand. They don't need to increase the energy because with the same energy, they can supply the population. And on the other hand, this country have a very minimal increase in population. The birth rate in these countries practically is zero. In some of them, they are negative. We see in contrary that in China, India, Southeast Asia, Middle East, and Africa, and Central and South America, the increase is dramatically. And increasing dramatically in energy because all of these countries are now concentrated into increased energy using any possible source to do that. And they are not concentrating also much in reducing the CO2 and what is important, doing better condition on the process production. That is to have more efficiency in the time that we produce that energy. So for that reason, we see here that in the world at the moment, still oil, gas, and coal are the three main dominant players. Nuclear is only 6% and renewable is 13%. But from that renewable 13%, we see that we have a big crunch that is called bioenergy, that here is where biomass is coming into effect. From that bioenergy produced, we see that waste biomass is only a minimal part. Practically 90% is coming from biomass that is coming from the burning of trees, wood, and the burning on biomass material in order to produce heat, in order to allow in many countries people to cook, because they don't have the other facility. So what we need to do here is to reverse that, to increase the bioenergy and to increase the renewable amount, and at the same time to use increased into the waste material rather than to use to cut trees and use the biomass that it can be used into another way. Biomass is important, and just here a brief some history of biomass. It's not something that we are saying now. We like to replace everything by biomass. We like to do process by chemical process and obtain chemical from plant. This is coming from a long time ago, in 1850, starting with ethanol for lighting, and then it went up to the First and Second World. The thing is, this whole industry was shifted out and it was closing because of the advent of the oil industry. That was just coincidental at the end of the Second World War. But you see here that, especially in the States and in Europe, the biomass and the fuel and the liquid produced from biomass as a fuel, they were used very, very efficiently, especially also in the first car. The Ford company used into the first car that they produced, the 4T and the quadricycle. So it's nothing new. What is important to know is that there are opportunities. The main opportunity is we can reduce CO2. We have a global amount of biomass that is tremendous. Biomass is the largest sources of carbon that we have terrestrial. And the problem is, it's not a problem. Biomass is everywhere. So there are not a strategic condition for any country. Any country has biomass. We don't need to import. Biomass has three main components that are the cellulose, semicellulose, and lignin. I will show you later. This is not digested by human. Consequently, we can use very well the use of this component for the valorization into chemicals and fuel, and at the same time use the biomass that can be used for food supply. We can just separate the two conditions. It's costly, yes. If we say that at the moment, if we like to deliver energy by biomass, is on the basic, for example, of $85 a barrel of oil equivalent, that is today. Today is between 85 and 90, the barrel of oil. Into the current price of the biomass, we just be up to there. We will not can make break even. The best way to do is that the oil continue rising, because when the oil price rise, the other energy commodity prices also rise, like the gas and the coal, because we need to compare between the three. But we can do that. And in the US, it's predicted by 2030, 20% of transportation fuel and 25% of chemical can be produced by biomass. This is a good idea. We see is the present government continue with that policy. Biomass is solid, so here is the challenge. We need to design new process for that. If we like to use the current technology that we have, the present of the current chemical plant and also refining plant for oil, we need to do arrangement and we need to design different process, different conditions in order to treat that, because we are talking about solid. There are issues with the production of biomass, certainly. The first one, as I mentioned before, is food supply. We cannot use any biomass divert from the use as a food supply to use for energy in order to produce chemical or in order to produce fuel. That happened in the past, yes. With the first generation, people starting using in order to produce biodiesel and to produce biofuels, they were using crops that they were used for food supply. What happened then? Prices increased, and we have very low demand for food in that case, and it's a big disruption in the economical of the world. The other condition is the competition for land and water resources. This is ours in very high demand, especially if we like to use a particular biomass in order to produce particular product. We need to look into that. If that biomass can be planted every year, we need to do rotation. How much water we need to supply. This is our condition. That they will be affect the environment because we lost biodiversity. Produce, if we cut tree, for example, like happened in the Amazon region in Brazil, we have soil erosion. We have this deforestation is causing disruption in the rain system normally that happen every year. And now the big rivers are practically dry. This is crazy, what is going on with this situation. For that reason, we need to be careful, develop technology that will lead a generation of conditions for the applicability and creation of new chemicals, but taking into consideration these particular issues. If we see the evolution of biomass into fuel and chemical, we see that we went from, as I mentioned before, the first generation, we have the cereal, the starch, and the sugar and the oil crop. This is all used for food. But people were using to produce biofuel. That was in 2002 up to 2005. They produced a big disruption of prices and then demand and supply into the food industry. For that reason, we move into the second generation, what we said, from now on is only use of all waste, municipal waste, industrial waste that can be used, manure, and everything that is not in the food chain. Coupling with that, we are now getting into third generation where we said, okay, there is also algae biomass, that is algae biomass can be used also very successful for the generation of protein, for the generation of chemical, and for the generation of fuel. And the fourth generation we are looking into the future, into the 10, 20 years, is to genetically engineering new crops and new algae material and create a specifically designed microorganism in order to produce a specific target chemicals that they can be supplied in the market by this way. This is how we are evolved the conversion of this process of the biomass. We need to take also into account the energy efficient. If we take biomass without we take a plant, you drive the plant, and then, for example, you burn the plant, you produce energy. Biomass have not much efficiency. Okay, it's more energy efficient than coal, oil, and natural gas, but it's very low in efficiency if you compare using solar, nuclear, hydro, geothermal, and especially wind. Okay, so into the renewable family, biomass used as it is the less efficient, because only 52% can be energy efficient and can give half of the energy of the plant. So the other is lost. So for that reason is, do we use in that way or how we can process? Talking about that, we need to take in the biomass sources. As I mentioned before, we are concentrating now here, especially in Australia, only to use waste. It's coming from the forestry, crop, and residue. Everything that is produced in the forestry, we need wood in order to produce furniture and so on, floors, and so on. So every that is waste from that, we can use for transformation. The same from agriculture and crop residue. That is a very, very abundant, especially here with the sugar industry and also with the crop industry, maize, sorghum, and so on. Sewage. Sewage also is a very important source of biomass and could be industrial sewage, municipal sewage, and also the medical sewage from the hospital. Industrial residue, animal residue are important, especially for the biodiesel was previous years in which you can use the tallow from the manufacture of the meat, and also you have municipal solid waste that always people throw furniture and throw that is made of biomass material. So that municipal solid waste can be converted also as a source for biomass. Biomass is different if we compare with the traditional petroleum, because petroleum is always high thermal stability, very volatile, and low functionality. It's very stable. Biomass is poor stability, totally contrary, low volatility, because it's solid, and have too much functionality, excess functionality. In that particular case, we need to create a new paradigm of process if we like to work with this material. This is a slide that always I put because I love this slide because it's giving you a process comparison between what happened now and what will happen in the future. On the left-hand side, you have the petroleum industry. That is something that we know for more than 100 years. This is very well established with all the process, with all the factories. And we know here that this is very easy to do. We have process already in place that produce either the fuels or produce the chemical. You see on the right-hand side that if we have biomass, we have totally different conditions. One is liquid, the other is solid. Biomass is solid. The reaction that we have here are totally different. In the other one, you do a very simple fractional distillation of the oil in fraction and then you process. Here we need to pre-treat and we need to break into platform molecules because of the configuration. And then because there are small molecules, we need to adjust molecular weight. And one of the problems is the oxygen. We have a lot of oxygen. If we need to produce fuel, fuel doesn't need oxygen, the same that chemical, very low quantity because of the reactivity. So here we need to reduce the oxygen, we need to increase molecular weight, and we need to do some reaction called hydrolysis in order to break that are totally different than petroleum. And then is the family of new reaction that there are organic reaction, aldocondensation, dehydration, oligomerization. And one of the big problem here is we need to produce also hydrogen because we need to be sure to be independent of the fossil fuel. And the process needs to be continuous. It's a solid, so how we can do that? If we see the structure that we have of the biomass fraction, there are three main components, the cellulose, the hemicellulose, and the lignin. The more prevalent of that is the cellulose. And the cellulose is the most difficult to react because it's very crystalline and is form of glucose. That is a polymer of glucose. Very crystalline structure, 100% crystallinity is practically impossible to break in normal conditions. So we need to have a very special reaction in order to do that. The problem is that the lignin, the cellulose, and the hemicellulose are tangled together. And one of the first things that we need to do is how we break them. Because the cell wall structure of the plant is formed by the lignin. The fibers are mainly from the hemicellulose that is embarked and is covering all the cellulose that is at the center. So that is what we need then to try to break. And why this is important? Because depending on the feedstock that we are working, we can produce what we call high volume and low value. The high volume, that is commodity chemicals, they have low value in the market. And that can be produced mainly from the three components, the cellulose, the hemicellulose, and the lignin. But if we're going into produce a specific pharmaceutical chemical, for example, a specific pharmaceutical drug, we need to have a lower volume where this drug has very high value price. And in that case, we need especially potential part of the biomass. We need to be very selective on what we choose in order to do these reactions. So this being important, we know that we can create what we call the fractionation tree. So if we can fractionate all the source of the biomass that are there at the root, that could be grass, could be coniferous, that is wood, and could be deciduous, that is a combination of both. And we do a fractionation and we can separate the three of them, then we can have a different industry. It doesn't mean that we need to go in one process with everything. We need to choose. And we can produce plastic, pharmaceutical, we can produce chemical industry products for agriculture, nylon, we can produce carbon material, and we can produce a complete chemical industry. But to do that, we need to understand that it's fundamental. and we have a challenge here that we need to solve. We have the complete structure of the biomass. If we don't do a fractionation and we don't do a separation, then we cannot go into this reaction. So we cannot work, as I mean, with the plant. We need to do pre-treatment. And this pre-treatment is the one that I will show you are the most expensive part of the process. Why we need to do that? Because if we do that, we can separate the three components, the cellulose, the hemicellulose, and the lignin. And as you see here, the cellulose is this conglomerate and polymerization of the glucose, very structured, very rigid, and very crystalline. The hemicellulose is a combination between 5 and 6 sugars that they are not totally crystalline, are more amorphous. And the lignin are totally different, are based for aromatics. There are aromatic compounds joined by oxygen. That is meaning if I like to produce aromatics, I cannot work with hemicellulose. So first I need to separate. That is why it's important how we structure the condition for the separation of this material, because we need to go into the specific product. For that, what we can use is material that we call catalysts. And this is our material that are solid, and they join with the part of the biomass, and they do a particular reaction. They have functionality because what they have this material is that they have property to conduct a specific reaction. As soon as we know that we have this particular feed and we like to produce this particular product, we can choose one of these materials. These materials are very selective. It's not one material that can be used for all the type of biomass, and it's not one biomass for all the material. No, we need to see what are the functionality, what reaction can be they do. They do oxidation, they do hydrolysis, they do dehydration, and they do hydrogenation. So what are these catalysts? For the audience that don't know about catalysis, I will say that a catalyst is a material that you put in a reaction in very small proportion, okay? Normally is 1 in 100 of the total volume. And this material will be just going into the reaction, will be accelerate the rate of the reaction, will be allow a selective condition or chemical that is the feed to be transformed in a particular product. It's very selective. And at the end, you can recover the catalyst. This is the cycle. Start because they have these functionalities. One reagent here is going here, then take another one, attach there, then go into the reaction, produce the product go, and we recover the material. These are very important. These materials are functioned for more than 100 years. And these are the base of all the chemical industry now and all the base of the petroleum refining. So that is how we create chemicals and we create fuels. So we can apply this material for our reaction also that we have in biomass. The characteristic is that this catalyst will be unchanged at the end of the reaction, and only one small quantity will be required. As I said, it's only 1 in 100 normally. And don't change the equilibrium, don't change the value of the reaction, but will be improve a lot the condition to reach the equilibrium. How do you attain equilibrium? Increase the reaction rate. So the time for conversion between reactant and product is very minimal. As I said, they are very specific in nature. That is meaning every reaction needs a specific catalyst, and they exhibit maximum activity at particular condition. For that reason here, we need to have a tag, the feed, the catalyst, and the reaction condition, and where we conduct, what is the vessel that is called the reactor. So it's a conformation of different conditions for a particular process. This is just to show you that if we use this material, yes, we can develop and we can plan a conversion from the feed, that is this biomass stock cellulosic material. Remember, I'm not talking here to put a mixture of them. No, you can take one of separately, and then depending on the chemical structure, you do what we said before. We can do the separation. If we don't like to do the separation of the cellulose, hemicellulose, and lignin, we can do thermal reactions, and at the end of the day, we can obtain different products using different particular paths of reaction. For example, hydrodeoxygenation. We remove oxygen and we put hydrogen. We can do aqueous phase reforming processing in order to obtain alcohol and alkane and fuels. We can do esterification, hydrogenation, dehydration. We see that this particular reaction then can be done very efficiently. And one of the ideas is now that we don't need to build new plants. We can use the reformulated plant that they are using at the moment, the oil industry. The petroleum refining, the refinery, can be very sweet to do the reaction. We modify just part of the process and we work together. This is the idea that we have. Working in conjunction with the oil industry in order to start bringing renewable into their industry. And they, at the end of the day, will be phase out the fossil fuels and will be going more and more into the biomass conditions. If we can do this, then we can create what is a biorefinery. In a biorefinery, normally you take the condition that we have here. These are the feed, the different biomass feed that we put: sugar crop, starch, grass, lignocellulosic crop, residues, organic residues, and then depending we do separation, pretreatment, or whatever, we're going into a particular path where we can produce either the C5, C6 sugar, cellulose, hemicellulose, the lignin, or we can do directly everything together with the lignin, heating that, produce pyrolytic lignin, then generate electricity, or we can produce oil that we can produce then different products from biomethane, from chemicals, polymer, resin, electricity, food, and so on. So this is normally the complexity of a biorefinery. At the moment, a biorefinery, that the most typical one is the one producing ethanol. Ethanol fermentation from sugarcane, and they produce ethanol and produce different liquors, and they produce with the bagasse, with the residue, they produce animal feed and they recover nitrogen for fertilizer. This is normally how classical is at the moment a refinery that is working for more than 50 years. So this is a typical one. But what we like to do is to incorporate process now that can then replace slowly the chemical industry, what is doing at the moment, and some of the processes that they use are very contaminant for the atmosphere. They have a very high contamination, and also they are very corrosive because they use acid. So if we can do this, then we create what we call value change. And this is an example what we work and study here. We get from the input of the feed what we can get downstream. Do we have the chemistry and also the energy into the power and heat? How we do that? We are dedicated into use artificial now intelligence, and when we use this, we use complex neural network in which generate algorithms that we can create this neural network of reaction that at the end of the day, we can optimize the intermediate here and the final value of the product and the compound. So what we are doing is we then put together an economic approach in how we can extend from the feed, that is the input, into the downstream chemistry and select the particular chemical that we can produce and we can effectively produce using the artificial intelligence network. If we do this, then here we're going to see now how we can have a strategy. We know that with the lignocellulose biomass, we need to do a pretreatment. Doing the pretreatment, then we do reaction like hydrolysis, or we do biological enzymatic, and then we can get the sugars and we can get the lignin separately, and then we can produce product. All of this base technology can be used if we like to produce any sort of intermediate platform molecule, okay? This is in the middle here at the platform molecule. And this one, then we can manufacture more important chemicals that we can create the market. This is the idea. In order to do this, we have challenge. but this opportunity is a new beginning. The big challenge are the biomass feed pretreatment. This is one of the big issues, how we do that, and we need to do in a correct way. Value chemical from carbohydrate. This is also what chemical we can produce from the cellulose and the hemicellulose that are the carbohydrate. What we do with lignin, how we valorize the lignin. How we can transform triglyceride and fatty acid if we like to produce green fuel. Do we do the classical biodiesel, continue doing that, or we produce a more formulated fuel? If we not do the separation because the pretreatment is very expensive, how we can do the thermal and catalytic fractionation? And the other point is hydrogen. Do we produce hydrogen from biomass? It's a lot of talk now at the moment, and especially here in Australia, we are talking about blue and green hydrogen. The blue hydrogen will be produced from natural gas. The green hydrogen will be produced from biomass. And it is expected that Australia in 20 years will be a big market for hydrogen. Hopefully, with the government intervention, that could be a reality. So I will just touch this point briefly. And the first thing that we like to say is, okay, first, as we said, we do with artificial intelligence, we have a biomass feedstock and we classify the biomass feedstock in groups. How we do that? Okay, we get information from the literature, we get previous information from project, and we divide it into different groups. For example, industry waste, biofuel crop, agriculture waste, and oil crop. Everything going, for example, into these 4 groups, and then from these 4 groups, we see how we treat it. We don't go in all together. For example, if we're going into the industry waste, we have paper and pulp industry, kraft lignin, and lignosulfate. So this condition then, this is our product that are obtained in this industry, that these one are compounds that are not used. How we can improve that? The same with the biofuel crops, the agriculture waste. The agriculture waste is the big chunk of material. And then we have the oil crop, the one that are not using in the food chain, that also can be contributing for the production of chemical and fuel. If we like to work with them, then one of the conditions is that we need to do biomass pretreatment. Pretreatment is very crucial because we need to separate the cellulose, the lignin, and the hemicellulose. Because if we don't do that, it will be very difficult to produce the chemical, and the catalyst that we use, why that the enzyme in biological process, enzyme are biological catalysts, are the same that the chemical catalyst. So we need to do this biomass treatment. Biomass treatment is considering the most expensive part of the whole process. So for that reason, if we don't do this right, then the other part will suffer. Because there are different factors that we need to consider. What is the stock that we have? How can we process very large fish stock? For example, we have bagasse, or we have agriculture crops. How we work with that? We need to use probably 2 different pretreatment because there are 2 different components. How we reach the high yield regardless of the type and the origin of the biomass. When we don't have a particular biomass from one source, can we still supplement from another source? How we eliminate the waste and toxic component that normally could be in this biomass waste? Yes, because of the pretreatment that they do previously. So we need to see how efficient we recover the different fractions, and then the more important is reducing the cost of equipment and energy demand. In order to do that, we need to know exactly how the plant works, from the real plant to the microfibril that are consistent of the 3 components. So we have the biomass, the plant cell, the microfibril, and the macro and micro. So in the macro is where the lignin is, part of the lignin, nearly 60%. The other part is entangled between the hemicellulose and the cellulose. In order to do that, then we can apply also another analysis that we do using these particular equations, in where we have evaluate the composition. And evaluate the composition is very important because here we can very simple and by a statistical analysis determine what is the main component. It's not only the cellulose. In some of the material will be the lignin. So for that reason, that material can be directed for lignin. For example, if we have softwood have more than nearly 30% lignin. The agriculture waste, the lignin is very low, it's half or less. So it's more cellulose. In some of them, they have more hemicellulose. For example, like oaks and hardwood and poplar. But then how we separate that? If we know that composition, then we can work for the strategic pretreatment. And the more important is the condition of oxygen, how much oxygen is in the biomass. Because as we compare the biomass has very large oxygen compared with the traditional process. So we need to eliminate that oxygen. Normally it's in the quantity of 45–50%. And this oxygen need to be decreased. If we like to produce fuel, oxygen need to be zero. Fuel and only hydrogen and carbon. Unless it's biodiesel, that is totally different fuel that is here, for example, and is more in consideration with the biomass. So using all of this information, then what we do is we have different ways to do the pretreatment. Pretreatment can be done by chemical means, physical-chemical. The two of them are combination with also thermal process. Chemical is you have acid, you have a base, and you do a pretreatment in certain condition in the separation. Also, you can use organic solvent. You have the organosol pretreatment. You can use ionic liquid, yes. You can use solvent, deep eutectic solvent, and you can use an oxidative solvent. Physical is more strong force, pressure and temperature, mechanical, microwave, ultrasound. But then you can combine the chemical and the physical. It's very energy intense because if you do a steam explosion, or you do ammonia fiber explosion or liquid hot water, this is consume a lot of energy. You need to take into account that. How extend need to be the separation of the three components. And then you can do combination. Microwave is a good technique, but the problem with microwave, we have also the energy intensity into a big industrial scale. So all of this treatment can be applied. After we apply all of this treatment, then we can get the three components separate, 3 or 4, depending on the condition of the plant, because we need to know exactly what is that composition. Where we do that pretreatment, okay, I show you some of the facility that we have here. This is more for physical pretreatment. This one are more chemical pretreatment. So, and then we use different conditions. We disrupt the natural structure of the fiber with this pretreatment. And for example, we have using glycerol, we have the license to a company. We develop another one using alkylene carbonate and glycols and ionic liquid. So using this pretreatment, we do the separation into the different fractions. And then they can be used for different processes. This is how pretreatment is done. After you've done pretreatment, you have the different fractions separated. One of the first is the cellulose. The cellulose, as I said, is the most abundant organic compound that we have in the biomass structure. It's normally 50% or more. It's a linear polymer. It's very complex. It's very difficult to react. It's unreactive, and it's very recalcitrant. There are composed of glucose. So if we break the cellulose, we get glucose. And the glucose is very important in order to continue transforming into chemical. The problem is we have two different bonding, the beta-1,4 glucosidic and the beta-1,6. The beta-1,4 is the most difficult to break because it's the one that is between glucose and glucose. And it shows there in the graph. The beta-1,6 is the most easy to do that. And depending how do you break that, is that the different sugar component that you will get into the fraction. The second one is the hemicellulose, and the hemicellulose is a compound that basically is amorphous and is a combination between C5 and C6 sugar, mainly C5 sugar. So it's very easy to break, it's very easy to separate, and one of the good things is soluble. It's very soluble in water and it's insolvent. So we can separate the hemicellulose fraction from the cellulose fraction that is not soluble. And The third structure that is in the fibers and in the fibril is also called the silans. That is similar to the hemicellulose, but has the particularity that they have another group joined together, like the acetyl ester, glucuronic acid, arabinose, and also they have some of the aromatic compounds that are part of the lignin structure. So this is a more complex nature structure with the ramification that they have. And this group also can be together with another group in another part of the plant. And it's very difficult to know the structure of the silan. Recently, in Nature was a very good paper that at the end of the day, they get the relationship between this chemical structure and the origin of the plant, because this is one of the problems, the origin of the plant, and I will show you with the lignin. The lignin is the fingerprint of the plant, and the silan is the second fingerprint of the plant, because they tell you exactly the structure of the plant and the age of the plant. And what is important, what is the origin of the plant? This is what the botanics people are doing. So if we do the separation of the cellulose and the hemicellulose, the two main compounds are the glucose and the xylose. Xylose is the C5 sugar, glucose is the C6 sugar. 6 carbon and 5 carbon. What we can do with them? With them, there are two compounds that at the beginning are the one that we produce, that are the HMF, 5-hydroxymethylfurfural, and with the glucose and with the xylose, the furfural. These two compounds are key compounds in the biomass industry because are the key compounds that from them you can flourish a large amount of chemical. You can produce, for example, here, sorbitol, gluconic acid, saccharide acid. You can produce compound that going into food industry and also in pharmaceutical, or can produce from the furfural, the xylitol, silonic acid, silaric acid. What is important from here is I will show you that you produce also another compound like plastic and fuels, and that is why is the key condition of this. If we look into the furfural and the HMF, this is the HMF and this is the furfural, we see how the two of them can connect. And at the end of the day, there are compounds like this plastic at the top and this plastic packaging at the bottom, and also the fuels here that can be produced by a certain rate of reaction that can be performed when these compounds are in contact with a catalyst, a particular catalyst that they have a particular property. For example, this one is a metal, one metal copper, second metal ruthenium, that is in combination with carbon, and then in contact with this one, with the HMF, a particular condition, particular temperature, pressure, and time of reaction, you can produce this compound that there are few functionality. I said one of the compounds important here is 2,5-furan dicarboxylic acid. This is known in industry as FDCA. This is the one that is producing plastic now and is producing plastic packaging. And this plastic packaging here is very important because it's renewable and biodegradable. Who is using that? One example, Coca-Cola has 75% around the world, and all the packaging, the bottle of Coca-Cola, plastic bottle are produced using FDCA. So they are doing something very good because this bottle of Coca-Cola can be recycled already, or if they are thrown away into the environment, they degrade in 2-3 months. And they don't produce contamination. This is the other great thing. You see here that how very easy it was coming from the biomass, do the pretreatment with the glucose, produce the HMF, and then going and produce these things. This is, for example, the SDCA. You see, this SDCA is very simple. The biomass, we have the cellulose, we do the hydrolysis, pretreatment, we separate glucose, and then we isomerize into fructose, we produce the HMF, and with a correct catalyst, we're going directly into FDCA. Very high thermal compound, is very sustainable, 100%, very lightweight, and is for hot filling, and also is 100% recyclability. And the shell life is improved at the transfer rate versus the PET, that the PET is the normal bottle of plastic that is produced from the oil industry, from the refining, from the petrochemical. This is a good example, how we're going from the root of the plant into something very valuable. And at the same time, if we don't produce this plastic, here we can produce what we call alkanes. The same HMF do aldo condensation coupling, produce this compound. In the presence of hydrogen, they produce this saturated compound by dehydration, and hydrogenation produce liquid alkane, and from here is a route for jet fuel. This is another important process that is at the moment under study. We see here that from fructose, we have this compound that is nominated one of the 12 more important chemical compounds from biomass by the Department of Energy in America, or either we go into this one from the polymer or we go into the liquid alkane fuel. Very simple example. If we go now to the lignin is totally different. When we separate the three structures, we have lignin also. The lignin is nothing else than aromatic compounds joined by change of oxygen, an oxygenated compound. Lignin is produced by three different alcohols, the coumaryl, coniferyl, and synapyl alcohol. These are the base structure of the lignin. And because the lignin is so different, we call the lignin the fingerprint of a plant. That is meaning the lignin, what we do is every plant, if we know the lignin, we identify the plant. There are around in the world nearly 300,000 plants, so we have 300,000 structures of lignin, but we not use all of them, okay? So what we do is we separate again the lignin from the different waste that we have, the crops, the wood, and so on, and then we see how we can deconstruct that. Normally, the lignin in grass is more primitive structure than the lignin in a tree. The lignin in a tree is the trunk of the tree, it's very hard lignin. The other one is very soft because it's the grass. The particular is the lignin is interrelationated with the hemicellulose and the cellulose. It's the intercalation of this molecule. So when we need to do the pre-treatment, we need to do very efficient in order to break the condition. Normally, we don't reach 100% breaking of the tree fraction. We have a small quantity of each of them in every fraction, but we reach very high quantities of individuality. So the lignin has one particular thing that is also how we can treat it. The lignin can be used using pyrolysis. That is meaning, doesn't matter. We do a thermal process, hydrogenolysis. We break the lignin. That is meaning we obtain the monomer of the aromatic. We can do oxidation, gasification, combustion. There are three main branches here that we can produce. Biochemical is the most effective that we want to do, the more difficult. This is, we are now, still is not industrial plant for biochemical from lignin. So this is just in laboratory scale. We can produce biofuel. This is our in pilot plant studies. And bioelectricity is regarded as the most easy way to do it because you burn the lignin and you generate electricity in a generator energy. So, but is the less positive for the economy because the value is the less one. We need to go into high value chemical, that is that one. So we see here that we have the lignin, we need to decide the process, what are the products and the use. So depending then on here, if we like just bulk, or we like a specific one, or we like electricity, so it's how we generate and how we convert. The main problem with lignin is the isolation, as I said, because it's intercalated, and then how degrade during conversion, because during the pretreatment and then during the process, the lignin, due to the high content of oxygen, is very active, very reactive, so degrade very easily. So for that reason, we need to take into account those conditions, and especially in the way that we separate. At the moment, in industry, there are two particular ways to do it. One is the way that we separate cellulose and hemicellulose, and we disregard the lignin. So that is what when we produce what we call technical lignin. The other way is the one-way approach, in which the cellulose, the hemicellulose, and the lignin are separated in a way, in a mild way, that the three of them conserve the structure. When I mention technical lignin, it's meaning the lignin that is produced by a chemical process and is totally modified from the original lignin that is the natural lignin. So the two of them suffer in what we call degradation and conversion. The structure are totally different. I didn't put any different here because this is not a course for lignin, but take that into account. The technical lignin is very unreactive, very difficult to convert, very difficult to separate. Normally people, they use mainly for burning and use pyrolysis and produce bio-oils. The other one, the one that we can separate, yes, you can produce separated compound. Why is that? Because it's a very high value chemical from lignin. And we see here, high-grade lignin is the one that we can obtain from the plant and separate, is the one that produces the chemicals. The one that's from the organosol, the kraft, the lignosulfonated, that this is from the pulp and paper industry. This is our technical lignin, and this one is mainly for carbon fiber, some phenolic resin, activated carbon, some phenol, or going into the refinery. This is very low value. And then it's a low purity lignin that is when it's more harsh at the pretreatment, is only burned for energy, bitumens, or biofuel. So the one that we like is this one, the high-grade lignin, that is the natural lignin of the plant, because that is the one that you can manipulate and you can break the bonding. So there are different steps then from that. If we do the pretreatment, produce this technical lignin, and this technical lignin, then what we do is normally we put in pyrolysis and gasification, and we produce here either by Fischer-Tropsch methanol synthesis, we can produce fuels. If we treat it differently in two steps, we can produce chemicals. Or another new technology is the one that I said is we treat with catalysis in a very mild condition, low temperature, to produce and separate particular chemical compound, like vinylene is one, that is a very soft compound, very expensive one that can be produced very easily by the lignin, and some monomeric phenols that they can go into the production of plastic. The cellulose and the hemicellulose can be separated. So this is the general strategy. And as I said, if the lignin is produced industrially, technical lignin, we see here this difficult to separate and is more condensed. Here, normally, as I said, this is industrial lignin that coming from alkaline hydrolysis, acid or solvent-based process, that all of these processes are used for many years and are producing mainly pulp and paper. Depending the different quality of the paper, the different process, and the process is more corrosive sometimes. This is one of the problems. That is why now all of these very high quality paper for books and magazine, glossy one, are practically not produced anymore because of the level of contamination. This lignin is contaminated with acid, is contaminated with base, very difficult solvent like methanols, and very corrosive, that there is no point then for processing. And the point is how, where we put, you cannot put the lignin, the solution in a river. So you need to deconstruct in such a way that will be not toxic, but still that is not the case. For that reason, this industry are now more in a phase out rather than in an improvement. So for that reason, the idea is going into for an integrated biorefinery, going in what we call the first lignin approach, where here, yes, we have the cellulose and the hemicellulose and the aromatic ester and monomer separated. So this can be done. No, we don't use any solvent, no acid, no base. It's a very low temperature process, very low pressure process. We use the presence of the catalyst. We can use palladium carbon. We use another cheaper catalyst now. And in the presence of an alcohol, no corrosive like propanol or butanol, and not using hydrogen, using atmospheric oxygen, we can do this process separation. We get a residue that then We separate the catalyst. As we said before, the catalyst can be separated after reaction that can go into fermentation and can be produced biofuel and chemicals also. So then from that also, when we use an organic solvent and we have the lignin, not at the level of the lignin from the pulp and paper industry, but we have, for example, softwood materials and hardwood material that are coming from waste, or municipal material that are furniture in not anymore use, they can be separated, the lignin, and here we can do a depolymerization. We need to break the carbon-carbon bonding between the aromatics, between them and the oxygen, and we can do cleavage of the carbon-oxygen, and we can obtain monomers. This monomer then can be put into a reaction in which we do an oxidation and ring opening, and we can produce this compound that they call quinones. And by repolymerization, we can go into a big variety of products. For example, nanotube, resin, polyurethane coating, fuel additive, or fire reactor. These materials are bulk materials, and they have their value, but they are not the value of a commodity material. They are not very specific chemicals, because it's impossible to produce a specific chemical from a technical lignin. These are the two different conditions on the lignin. Vegetable oil. The vegetable oil is used for many years, and is used for the production at the beginning of biodiesel. Here they use vegetable and animal fat, that is the tallow, that is all the grease that is coming from the abattoir where the animal is killed and then is fractioned the different part of the cut of the meat. And this tallow also with the vegetable oil can be used for the generation of the biodiesel. Biodiesel is an industry that started around 2005, and still there are plants in biodiesel. The majority of plants in biodiesel are in Southeast Asia. Very few are in America, and in Europe, the one that are phasing out in 1 or 2 years. In Australia, we don't have any more plant of biodiesel because it was impossible to put a biodiesel regulation where the biodiesel is used. And the other big problem is that if you use, I know it can be replaced by diesel, but then the insurance company for the vehicle that you are doing the transportation, that is a car, that is a truck, that is a tractor, they will not insurance because they claim that you are liable if there is a damage in the engine. That produces a decline, and they produce the collapse for the biodiesel industry. The other big problem with the biodiesel is that there are very few regulations. International regulation in biodiesel is not there. So that is like there are in any fuel, diesel or gasoline or kerosene or jet fuel. But biodiesel was a very good resource, and they have the potential that because you can process a lot of oil here that come from greases, animal fat, vegetable oil that are not used as a food, and also people starting using from soy. That was the boom of the soy. That in many countries, especially in Latin America, they were just increasing the plantation of soy in order to have this crop against the maize and also wheat. The big problem with the soy is that if you don't do rotation after 2 years, the soil collapses, and you have a big issue of fertilization. So, and in many of these countries, they didn't do that because this is a big potential. Last year, in the middle of the pandemic, that was June, July, the price of a ton of soy in the commodity market in Chicago reached $650 a ton. When before pandemic in January 2020, the price of the ton of soy was just $150. So you see how it's boomed that. Now it's coming back in the order 300, but it's decreasing. So, and where is going that soy? Yes, it's going to the Southeast Asia in order to produce biodiesel, especially in China. What is the reaction? The chemical reaction here is very simple. You have the fat of the oil, and you do a hydrolysis, esterification, or direct transesterification. In both cases, you produce the biodiesel, that is a methyl ester, plus you have a 10% glycerol. This is the big issue on the biodiesel. 10% of byproduct is glycerol. That is not, it's a crude glycerol, it's not very fine glycerol. They have all the contaminant of the process. Because the transesterification and the hydrolysis esterification is done into base or acid condition using methanol mainly as a solvent. So all of these materials are going into the glycerol. So it's very difficult then to separate the glycerol. If the glycerol is not pure, you cannot use in the food industry or pharmaceutical. And then they have the other problem is the glycerol is coming from tallow. There are countries that will be object that for pharmaceutical product. So it's a big issue in that case. What we do with the glycerol. Here in Australia, what happened is that people were not know what to do with this glycerol, and it was very difficult to obtain a pure glycerol that they need to dispose. They need to go in a particular pond and do a chemical treatment in order to degrade everything. That was very expensive. Then the price of the biodiesel collapsed very easily, and the plant need to shut down. What they did at the end of the day, they were selling the biodiesel to the refinery mixed with the crude diesel and processed as a diesel fuel, no value. So this is what happened with the biodiesel. Then what is the situation? Okay, in Europe especially, they were thinking that, all right, we have all of this vegetable oil and all of this tallow, what we can do? All right, one of the solutions is, okay, why we don't hydrotreat and we process the vegetable oil and the fat and we produce real diesel, real gasoline? Can be done, yes, it can be done. Because in that case, they produce what they call green diesel, green gasoline, and green olefin. They do a hydrotreater, catalytic cracker for the gasoline or the lye olefin. And in Italy, is now one plant working very well and is supplied by UOP, a Honeywell company, that they supply the catalyst and they supply the industrial process license. This reaction normally what is a decarbonization or decarbonylation. So what they do is they remove CO2 or they remove CO in order to remove the oxygen terminal of the vegetable oil, because the vegetable oil is just, as I show you here, have this terminal group here that have the oxygen. So they need to remove and they need to saturate the double bond. So that is what this process is doing. So this is have the advantage now that this component, the diesel, the gasoline, are very similar to the one you produce in the refinery and are acceptable for transportation fuel. Looking further into the future, this process also have the capability to obtain like olefins, like ethylene propylene. That this is a very important material as a feedstock for a petrochemical that can produce then using the same process that any petrochemical, a green plastic using a green olefin. This is a great advantage. So this is just what it was in a presentation many years ago. This was the main idea of the UOP. They were, at that time, they were doing this oil and grease into the catalytic cracker and this into the hydrotreated to produce the diesel and the gasoline. This was material in pilot plant, but they developed very easily, and then they get the idea that they can work in a co-processing mixture of oil and grease. So here the good is that we can anticipate that if we have tallow and we have vegetable oil, we can mix together. It's not like in the traditional biodiesel process that they need to be separately because the composition is different. No, here they're going into a rigorous cracker or hydrotreater that they will break everything. And they have a very good quality blending diesel at the end of the day. This is just the plant layout, for example, for this UOP eco-fining refinery. It's very simple, the process. the vegetable oil going into the reactor. They have a separator where they separate the water. They do a separation of the gas where they purify the hydrogen. The hydrogen is produced in the process, and this hydrogen can go back into the reactor because they need the hydrogen for the reaction. And then they have a separating column where they do the separation at different temperature, the light, the middle distillate, and the heavier, and they separate what is the gases, like gases, naphtha or jet and diesel. And the CO2 that is produced is totally 100% CO2 from a renewable process. So that is considered as a bonus also in that way. And what they do, the plant at the moment is imported vegetable oil, and they are moving into used vegetable oil. That is better. The vegetable oil that is used in the market, into the fast food industry. That is a lot. They do a pre-treatment with that. They put here, so they import all this vegetable oil that is going around in Europe from different countries in Europe is sent into Italy by road or by ship, and they use internally there. So they plan to expand to 10 plants in the next 5 years. So we see here that if we compare the biodiesel with this sort of new biofuel that is mainly totally different, it's not a transesterification or a esterification. So the second generation of biofuel are better because just produce fuel that they don't have oxygen, okay, and not oxygenated. This is the main constraint and the main argument that the companies have with the biodiesel, the presence of the oxygen. And then you don't need to utilize any good oil because here it could be, just as I said, the vegetable oil that is used in the food industry to cook food in the different outlet can be put here, very easy pre-treatment, and they use it to transform that. And the processes can be done in very large scale. Only that they are doing in a minor scale is because of the supply of this vegetable oil as a feed, nothing else. The other topic is that if I don't have the possibility to do the separation because the pre-treatment is very, very, very expensive, and the value to doing that will be not justified the separation of the different fraction of the biomass, what normally do is a thermal treatment. The thermal can be catalytic and non-catalytic. Thermal biomass treatment are divided in different groups. One is the hydrothermal liquefaction, catalytic gasification, supercritical water gasification, hydrothermal carbonization, or algae pyrolysis. The main difference is the condition and the product that you obtain. Hydrothermal liquefaction and hydro is the one that the output will be a biocrude. This biocrude is a mixture of different hydrocarbons still containing oxygen that they will need then another treatment, another hydro treatment in order to be converted into fuels. So it could be just a feedstock for a refinery. The condition on the temperature are very mild temperature, up to 400 degrees Celsius, up to 20 megapascal the pressure, and you can use catalyst or not. The use of the catalyst advantage is to reduce the amount of oxygen that is in the final product. Catalytic gasification, on the other hand, the output is to obtain just hydrocarbon gases, mainly methane. And with that methane, you can go into the production of another chemicals or produce methanol or whatever. The other one, the hydrothermal carbonization, in this case, you put the process in such a way that you only obtain a biochar. The biochar could be used then as a fertilizer. You can dope it with nitrogen compound and use as a fertilizer for different soil that need refertilization. That is how you can use the biomass. This is not new. This is just an example in 1920 that is produced. The Ford Motor Company, they have a thermal process where produce everything for the manufacture of the car. And you see there that they use just wood and with that wood, they burn it into a closed container at 540 degrees, and they produce the gas. They produce this called pyroligneous acid, that is where this bio-oil. They produce a tar, very heavy one, that was oil and pitch, and the creosote that we use also in the manufacturing company, and they produce the charcoal and briquette for the heating and to produce energy. So this is our idea that there are new, but they are coming now in a beta way, in a beta process way. So then here we see how the process is going and what are the main products. You take the biomass, and the waste biomass also can be used. In that case, you can do, with the waste biomass, you can dissolve the material in an aqueous phase, and you do a decomposition if you like. This is one step. And by recombination, you can produce the biocrude, that the biocrude then produce gas and solid. Or you take the waste biomass and directly convert it into solid residue. That is instead of the hydrocarbon thermal liquefaction, you do the hydrocarbon thermal carbonization. Depending on the temperature, pressure, and condition of the process, you produce mainly the biocrude, but with the biocrude, you produce also an aqueous phase. This aqueous phase mainly are organic acid compounds, okay? In the biocrude, mainly there are aromatic lignin type of compound, furanic compound, all of that. The acid compound and the sugars and some carbohydrate and in the aqueous phase. If you optimize very well the process, then you have the advantage because the aqueous phase can be used then to produce hydrogen. That is what they are doing now. So by aqueous phase reforming, so you can reformate, you can break this compound into hydrogen, the aqueous phase, and have hydrogen in the refinery. This is one of the advantages. So pyrolysis, this is the other technique, and this is more popular. Why is this popular? Because this is done without oxygen. Here, just is a thermal decomposition in a closed vessel at very high temperature, no oxygen and anything else. And you have, due to this thermal decomposition, you produce a bio-oil and very different chemical and physical composition. Here also you produce a liquid phase, that is the bio-oil, and also an aqueous phase that going the other compound, as I said, the acid compound and some of the carbohydrate. And depending what you produce, the bio-oil normally 65–70% fraction. Depending on the temperature condition, you can produce more bio-oil or more solid material that are discharged. And or you like to produce only gases. In that case, you need to go in very high temperature. You produce methane, hydrogen, carbon monoxide. So this is the pyrolysis. There are different types of pyrolysis. One is the slow, that for biochar, nothing else, not going into another fraction. The flash pyrolysis, that is very quick, is like in a fluidized condition. And then you have the fast pyrolysis that they will do a very high yield of bio-oil into 60%, 20 biochar, and 20 syngas. The flash pyrolysis is when you like to push the bio-oil. In some cases, you can produce up to 80% bio-oil. But this pyrolysis now, they go into what we call staged pyrolysis, in which you have a reactor that you work in the reactor at different temperature, and depending on the temperature that you have at the different part of the reactor, you are doing drying, torrefication, pyrolysis, or gasification. And you are pushing there then the separation of the different fractions. Why is that? Because between 300 and 400 degrees Celsius is very important fraction that we call, that is the furanic fraction, mainly furfural, and the sugar fraction, the anhydrous sugar, that is the levoglucan. These two compounds are very important products, because from here, these are base platform chemicals that will build a complete new family of compounds. And that is how people are doing, are targeting, maximizing the separation of these two compounds between the torrefaction and the pyrolysis. For that reason, they are staging the temperature moving into the reactor into this condition in order to get the maximization of the best fraction. They are not interested in the low fraction, that is the terpene, or in the high fraction that will be the phenol, methanol, and charcoal. They are interested in the intermediate. And the main reason is this is a new approach of the pyrolysis, okay? Before was the flash, it was the slow pyrolysis, but now it's done in a different way, in a particular new reactor design. And these two fractions are important because, as I see here, these are the different temperature that we can regulate the pyrolysis. It's one particular temperature, because this is the whole biomass, that mainly the hemicellulose will react is 150, 300. Between 200 and 400 mainly react the cellulose. The lignin going to 150, 600, so lignin will be in the other fractions. And the whole biomass is up to 600. That is when we produce the solid material. So if we control this fraction into that particular region here, we can very well separate the furfural and the levoclosan. And the reason is because with the furfural, we can develop, this is just as a demonstration of this industry, you can develop all the plastic that you can dream. And the same is with the levoclosan. The levoclosan is the base compound for a large family of chemical compounds that can be produced. That is, if we maximize then this condition here and we maximize this one, we can obtain a selectivity to this compound between 85 and 90%. The other part is not of value. We use in different things, but the trunk of the process is this fraction. That is what we call a stage degasification pyrolysis. All right. And the last topic, we say we need the hydrogen. Hydrogen can be produced by biomass. Yes, hydrogen can be produced by electrolysis. Hydrogen can be produced by solar energy, by wind energy, that then can produce electricity enough for the electrolysis. If you are lucky to be in a country that they have very large water resources and they have hydroelectrical dams, yes, you can put electrolyze and produce hydrogen. There are few countries of that. Practically 85% of the world is not in that condition. Then the hydrogen through the biomass can be produced through biological process, thermochemical, or chemicals. At the end of the day, the idea is to produce hydrogen. Hydrogen is a commodity that is very valuable. We said that we like to bring a hydrogen economy, but hydrogen is the large chemical that is in the world, but it's not as hydrogen. Hydrogen is normally in a carrier, a chemical compound, and then you need to deconvolute that compound and extract the hydrogen. So here we like to produce hydrogen as it is. One way and one vision that we have, because of the time I will not go into we said this is our technique, is to produce hydrogen into, if we treat a feed that is a waste, and using this hydrothermal liquefaction or hydrothermal gasification, we know that produce, depending on the condition, we like to process bio-oil. And with this bio-oil, we produce a small amount of syngas. We can produce the water fraction, and the water fraction, if we use what we call aqueous phase reforming. This aqueous phase reforming is the same reaction that the reforming reaction to produce hydrogen by the oil industry, okay, the refinery. Hydrocarbon reforming and gas reforming, that is the methane reforming. We can produce in aqueous phase. This is a new process that is very new, that can produce hydrogen. The same way, if we have syngas is CO and hydrogen produced from this reactor, we can use a membrane separation technique and we can have the hydrogen. The oil fraction then need to be hydrodeoxygenated. What meaning is, in the first catalytic reactor, we remove part of the oxygen. In the second process, we injecting hydrogen, we remove the remaining oxygen, and then we have biofuel to the market, and the excess hydrogen also can be the consumer. This is the dream, okay? This is what we call a new integrated process combination in which hydrogen and fuel can be produced. We try to put this idea into the government. We try to put this idea into the industry. They need to be developed. And I think we have the different parts. And that could be a breakthrough in biomass processing. This is just, I put due to the time, a few minutes, is an example. And this example is how we design a biorefinery. We don't go into very big biorefinery, but for example, if you have biomass and you need to upgrade, here is very simple. What we said is, okay, this is coming from bagasse, or coming from the pulp, or coming from agriculture crop. So what you need to do is to do a pretreatment, very easy pretreatment of the biomass. For example, in this example, if you read then, you obtain furfural, and then you obtain carbon for battery anode. So, and then you can do, how you do that? Okay, the first thing that you need to do is to create a flow sheeting, how to develop the plant, and from here, using artificial intelligence, depending, they give you which are the three main compounds that will be the key in economical benefit of the plant. If somebody is interested on this study, I can give you all the detail because it's a lot of calculation and so on. We see here it was determined that the pulp that can be used for another purpose, for carbohydrate, the lignin can be used as a carbon phone and then can be developed into batteries, anode, and the furfural can be used for chemicals. How we know that? Okay, we know that because we have a block diagram. This is what we solve. And in the block diagram, in biomass, it's very important to follow what is the course of the biomass, of the carbon. Where the carbon is going. We start with 100% carbon. So then we see here how carbon is going into the different process. And we see here that 37% is going into the pulp, 20% is going into the lignin, and only nearly 20% going to furfural. So it's better that this furfural produce a very good chemical, high value, in order to compensate for all of this process. So this is only an example how we need to do the model, the thermoeconomic. And this is what developed using Aspen Plus. It's very simple process simulator for engineering student, and it's normally how we design any chemical plant. The message here is we can do the same that we do for a chemical plant if we have enough information. And now with the tools of artificial intelligence, we can do for biomass, because we need to know what is from the beginning and what is the optimum achievement. Okay, this is just a demonstration. This is come into the literature. This is a plant, a biomass biorefinery plant that is now in functioning in the Netherlands. We see that things are going. Okay, there are a few of them, but it's important. People are moving on. We are doing that bridge between the fossil and non-fossil fuel. Okay, this is the summary. We see the potential here to establish the biomass as an industrial feedstock for the chemical and fuel industry, but we need to have a rational processing of this material into the application, and we need to look into the different feedstock that will be produced, the particular component. And the use of biomass, I know still is not cost competitive like the petroleum, because petroleum is developed for more than 100 years. But we need to do further development on the chemical process, especially on the reactor design. I didn't touch the reactor design, but normally I give a class on reactor design for biomass because the reactor design is totally different. And then the reaction mechanism, we need to study that for the efficiency and for the selectivity. And in that play a very big role, the catalyst that will be allowed to produce very simple materials and with very high selectivity and purity. That is what we want, that is normally done in the chemical industry now. All right, thank you for your attention, and is any question?
Professor Beltramini, thank you so much for your very stimulating and informative talk. I believe that the students gain a lot of insights and information from your lecture today. But we don't have time for
Yes.
questions and answer, Professor Beltramini. But so what I'm going to do, we're going to give individual homework to our students. We are going to post it to your Moodle, to the Moodle page. And please answer the individual homework until Friday next week. So you have, you will answer 2 questions about the, or 2 questions related to the lectures of Professor Susanna Yusuf and
Yep.
also Professor Beltramini. Professor Beltramini, I'm really amazed with the level of energy that you have. So you talk for over 90 minutes. It's more than the energy that we can get from biomass. Professor, thank you so much once again.
I have a good coffee before, so
I see.
thank you. Thank you.
Professor, thank you so much. I will see you again. And to the students.
Also tell the student if somebody need any particular topic or like to read more, they can contact me anytime.
All right, Professor.
If they are thinking to do any PhD in Australia, they can come to us.
Okay.
Thank you,
Fantastic
Professor.
university. And as I
Thank you.
said, we combine everything. We combine from the chemical, from the economic, and also from the IT now with artificial, because I'm now very enthusiastic with that topic. And I think that will be the solution. One of the parts of the solution of the problem. Thank you for your invitation. I appreciate
Thank you so
it.
much.
Yes. And I
We will
hope I can see you soon in Kumamoto. I don't know.
Right.
I tried to get things done in order to come back, but we see how our government is doing with that. Yeah.
Okay, Professor. I will see you again in December, Prof.
And
Thank
see
you
you
so
on
much.
the 17th.
On
On the 17th, yes,
Right.
in December. Yeah,
All right.
thank you.
To the students, thank you very much for attending this lecture today. And please check the Moodle for your individual homework. I will see you again next week. We will have Professor Cosero from Spain, who will give a lecture also related to biomass. It's related to the economy, biomass economy. So I'll see you again next week. Prof. Beltramini, thank you so much. All right.
Next week I will attend because I like economy.
All right, Professor Beltramini. All right. So I will send you the Zoom
Thank you
link
very
and
much.
also passcode. Thank you, students.
you.
Bye-bye, everybody.
Bye-bye. Bye-bye, Prof.
Dr. City, thank you.
Recording